Hello there and welcome to my channel. I'm Delirious. I'm independent security researcher performing solo audits, team audits and bug hunting. Today I present to you a mini series on EVM, which is foundational topic for any Web3 tech guy, be it smart contracts developer, security researcher or DevOps engineer. I share with you everything you need to know to read, review and write EVM native code. However, I won't spend much time describing topics like peer-to-peer, consensus nodes, and other topics not directly related to virtual machine executing the code. Additionally, there's a prerequisite. It is not an introductory course. I assume that you can write code in Solidity and have general knowledge on how blockchain works. If you don't, please check out Patrick Collins' full course on Solidity and read foundational topics description from official Ethereum docs. All additional materials are put down in the video description. Okay, it's time to dive in. In this module, I described EVM from the high level. This will make going through the specifics easier to understand. In this episode, I'll use Ethereum EVM illustrated by Takenobu, which gives valuable insights into EVM. But first of all, let's talk about what Ethereum Virtual Machine is. Generally, it can be thought of as a distributed state machine defining a state transition function. As you can see in this slide, we have some initial word state and we define state transition function, which in case of EVM is transaction. And after applying that, we are ending up with a new world state. Well, actually, transactions are not executed as a single entity, but are packed into blocks and then executed as a whole block. Selecting transactions that go into block are not restricted by EVM, and the validator preparing the blocks have full discretion over what goes inside of it. This allows them to extract additional value by putting the transactions in specific order, or picking the most profitable ones, or even creating and placing their own transactions in the middle to manipulate the outcome of the transactions. You should always keep that in mind and make sure that the contracts that you work on have proper protection against that. Next, let's discuss how blocks are modifying the world state. As you can see in this slide, each block provides update to the world state and each new block builds upon previous world state. So from the point of view of implementation, you can think about EVM as a chain of blocks. That's why the name blockchain. So what exactly is world state? In simplest words, the world state is a mapping between address and the account state. An account is a key object in the world state. It uniformly identifies single entity living within the virtual machine. Its identifier is an account address. In EVM, it's a 20 bytes long stream of bytes. Each account also consists of an account state. Account state consists of its address, which is its key, and its state. The state of each address consists of nonce, which is number only used once. In this case, its current number of transaction that is being executed. This is to prevent signature replay attacks because it makes sure that each single transaction has an unique identifier which is used once and then increased. Apart from that, address also has its balance. In case of Ethereum, it's Ether. In case of other EVM implementations, it may differ. Apart from that, each account has storage hash, which is just an index to account storage, and its code hash, which also is an index but to EVM code. And there are two types of accounts in EVM. One is externally owned account, which is owned by external actor. That means any user of the blockchain, can be me, you, whoever. And the most important part here is that it has private key from which public key is being deduced, and from the hash of public key an address is created. So externally owned account is just an entity that has private key and signs transaction with this private key. The second type of account is smart contract account, which contains code and storage. It by itself cannot initiate transactions. However, it can receive transactions and call other addresses. So in case of externally owned account, storage hash is hash of 0 and code hash is also code hash of 0, because externally owned accounts do not possess any storage nor the EVM code. In case of contracts account, storage hash is a pointer to the hashed storage of smart contract, and code hash is a hash of the bytecode that the smart contract consists of. So how do we determine which address an account have? In case of externally owned accounts, everything starts with private key. So the user generates private key for them, and from this private key, the public key is being deduced. Next, the public key is being hashed and the rightmost 160 bits are taken. Those are then treated as an address account. In case of contract accounts, we have two ways of creating an address. If the smart contract is created by create opcode, its address is taken from hash of sender address and the sender nonce, and actually the rightmost 20 bytes from this hash are taken. In case of create 2, the address is taken from the constant ff added with sender address, the sender provided salt, and ketchup of initialization code. And similarly to create, it is hashed and rightmost 20 bytes are taken as an address of the contract. And now that we know a bit about accounts, let's move to the transaction. So transaction is a single cryptographically signed instruction. And as you saw here, like only the externally owned account has private key to sign anything. That means that the transaction can be only created by externally owned account. In EVM, there are two kinds of transaction. One is contract creation. A second is a message call. The difference between them, technically, is in order to create a smart contract, you have to send transaction to the 0 address and have non-zero length data array. Otherwise, the transaction is treated as a message call. And in a message call, you can either call other externally owned account or contract account. Actually, on the broader level, EVM doesn't really care what you are calling. You can also call account that doesn't exist and it will be okay. Now let's look how contract creation looks more in detail. We have word state before contract creation, that we have some specific addresses and their state. And then we are sending transaction again to address 0 and non-zero data array, which signifies that this is the init code of the smart contract that you will use. And then EVM executes this init code and puts whatever it returns on the blockchain. And this is stored inside code. Additionally, if anything is set in storage, it is also added here. New address is being created, and now you have new smart contract. In case of message call, let's say that you are sending transaction to the address N and it has its account state with input data. This can be either externally owned account or contract account. And after this transaction, its state is being updated. As you can see here, code is not changing here, only storage. That's because EVM doesn't allow you to change the code under specific address. Of course, there are ways to work around that, but we will not talk about it here. If you are interested, you can check out how smart contract proxies work. But what the transaction really consists of, we already spoke about it having a transaction recipient, optional data, but what else is there? So each transaction has nonce, as I described before, to prevent transaction replay attacks. It also has two very important parts, which are gas price and gas limit. We will talk about gas a bit later, but in a nutshell, you are saying how much calculation expressed in gas you are willing to do and how much you are willing to pay for it. Next one, we have recipient, which is either address or 0 if this is contract creation. We have value, which is the native coin value. In case of Ethereum, for example, it's Ether. So if this was Ethereum, then the value would mean how much Ether you want to send with your transaction. Next, we have VR and NAS, which are transaction signature. This actually allows to prove that you are the person that wants to execute this transaction, because you are the only one that has private key. And if you are signing something, that means that you want to perform such action. And finally, we have data. In this slide, it shows us init or data, but actually this is just one field, data. But in case of contract creation, this field serves as a smart contract init code. And now on to the messages. Message is passed between two accounts, and it consists of data, which is just set of bytes, and value. And messages can be either triggered by transaction, which is what we spoke about before, or it can be triggered by EVM code. So smart contract accounts can also call other smart contracts or externally owned accounts. And this is all fine, but how do transactions land in this globally shared database? It is a bit tricky because at first it can be a bit unintuitive, because there is no single party that runs Ethereum Virtual Machine. Actually, you have multiple parties running the EVM, and they all reach the consensus of what the world state is. That means that you can think about blockchain as a globally shared, decentralized transactional database. So as you can see in this slide, when external actor is sending some transaction, they are using the interface to call the machine that is running the Ethereum node and which has current world state. And then each of the nodes communicates with one another to propagate the current state. Having shared state between nodes is great, but it poses some issues. And the biggest one of them is, how do you guarantee atomicity and order? And EVM solves that by having atomic operations. That means that the transaction either fully executes and everything is committed, or there is some error during the transaction execution and it's reverted to the previous state. EVM solves problem of ordering of transactions simplest way possible, and that is that every transaction has to be executed sequentially. There is no possibility of executing two transactions at the same time. But what about the order of transactions? If we have, for example, two external actors, and actor B first submits two transactions and then actor A submits third transaction, how do we guarantee that the order of the transaction will be preserved? Actually, we cannot. What EVM does, it keeps the transaction pool, which it calls mempool, and all the transactions that are submitted to the Ethereum node first are going into mempool, and then miner, or in case of current EVM state, the validator determines the order of the transactions. Usually, miners are incentivized by high fees. That means that if you are willing to pay more for executing your transaction, then you will be more likely to have your transaction included first. Now let's go a bit more into details around EVM architecture. Ethereum Virtual Machine has few main components. One of them is virtual read-only memory, where the EVM code is loaded. We have account storage, which is persisted, and we have the volatile state that is there only for the time of executing the transaction, and it consists of program counter, which is the number of current instructions executed. We have gas available, which just means how much more computation we are willing to pay for. We have stacks, where all the intermediate operation results are stored, and we have volatile memory. So going through a simple example, let's say that we have externally owned account that submits a transaction to swap some token A for token B. So at first, when the transaction is being executed, the call starts in the smart contract, EVM loads the smart contract code, program counter is set to 0, gas available to the gas limit, and then the bytecode is being executed. And during execution, it puts intermediate values to stack and memory. It also uses account storage to read persisted state, and the transaction goes on. If there is some state needs to be updated, for example, the user balances, it is being stored in the account storage, and then transaction ends. The EVM code is not required anymore, and all this machine state is being removed. And what's left is the persisted world state. EVM has multiple places where it stores the data during execution of smart contracts, and one of them is Stack. Stack can hold up to 124 elements. Each of them is 256 bits, which is 32 bytes, and it is being used for basically every computation that it does. If it adds something, subtracts, divides anything, most of the opcodes are using values stored at Stack to perform the calculations. Then we have memory, and next we have memory, and memory is just a volatile array. It differs from the Stack in a way that it can hold very long chunks of data. So for example, you can put there your whole contract or some long strings or whatever you want, which is not possible in case of Stack. And it's volatile, and it means that after the smart contract execution, the memory is erased. And finally, we have storage. This is what is persisted in the EVM world state. Storage consists of key to value mappings, and each key is 256 bits, and each value is as well 256 bits. And also you can see on this slide that there are no registers. Why is that? So basically you have two most common ways of building your state machine. One is register-based machine, and one is stack-based machine. Stack-based is super simple to implement. However, it requires much overhead over registers because you have like single stack where you are using all of your data for calculations. However, in case of registers, well, you have multiple of them, and you can store like intermediate values inside each registers and do calculations directly on the registers. However, it comes with a cost of complexity, and you will see that multiple times in case of EVM that the design is to prefer simplicity and security over like complexity and robustness. Going a bit deeper inside Stack, you can see it here that this is a 1024 elements array, each having 256 bits. And what is important, you have direct access to the topmost 16 elements of the stack, which I guess you fell into this problem before and you do not even know why. I will talk about it a bit more in details later. So as I already said, all the operations are performed on Stack. All the adds, multiplies, shifts, and everything that you may think. So you can access them with many instructions as push, pop, copy, swap, and others. We will go more into details of that later. Next, we have memory, and this is like a bit unfortunate because this is in this slide, it is depicted similar to the stack. However, you can think about memory more as a continuous array of data. And as I said, this is linear and can be addressed at byte level, so you can take one single byte from the whole array of memory and override it. There are only 4 memory-related opcodes. This is mstore, mstore8, which stores a single byte, mload, and msum. And each new memory that you are accessing is initialized to 0. Like basically everything inside of EVM, you do not have null values here. Default value is always 0. That's why you should be very careful when handling 0 values. And finally, we have storage, which is key value store mapping 256 keys to 256 bytes values. You can access the storage via store or sload instructions. And I will add here that this is the most expensive operation that you have. So you should do everything to minimize amount of stores and sloads. And why is that? We will go more into details about that when we will describe the gas and pricing. Finally, how the EVM code work. I have EVM codes open now to show you how the EVM code can be represented. EVM code is nothing more than set of bytes, and each byte value has like specific operation code, and each byte word has assigned operation that it does. So it can be shown as a mnemonic here. So for example, you see here this code that we have set of operation. First, we are pushing 1 byte, which is 42. Remember that 0x means that this is hexadecimal. Then we are pushing 0, storing it into memory. Again, pushing 1 byte, which is 32. And there is a difference. You can see it here. This is now 1x. That means that 32 is in decimal. Then again, we are pushing 0 and we are returning. These opcodes are in mnemonic representation. Apart from that, you may have bytecode. So you can see in bytecode the same situation. Number 60, which is push 1, and then 42, which means that we are putting 42 in hexadecimal to the stack. Then again, 60 and 0, that again mean we are pushing 1 byte, in this case, 0. The same thing, just different representation. And when you put it like that, this is how the EVM can understand what is to be executed, and the assembly view is for the reader to better understand what is happening inside of assembly. Okay, and just quickly to the execution model, how EVM works. So first we are loading our EVM code, and we are going through them one by one. Each time we are changing process counter, we are decreasing the gas available. Then we are pushing and popping from the stack, and having elements on the stack, we can now put the elements into memory or the storage. And let's quickly go through this specific code. Let's try to run it and let's see. So you can see here that we have process counter which starts at 0, and in our first step we are pushing 42. If we are going next, our process counter increased by 2 because we have 2 operations. First is push 1, this is our first byte, and 42 is our second byte, our second word. So we actually increased the process counter by 2, and you can see here in our stack that we pushed the exact number that we wanted. Next one, we are pushing 0. So you can see here that we have all of these values that we already pushed here, and we are calling mstore. Mstore takes 2 value. First is where you want to put something, and second of all is the value that you want to put. Okay, when we execute that, in our case, you can see that we put in the memory offset 0 the value of 42. And you can see here that process counter increased by 1 because mstore is a single operation. Next, again, we are pushing 20. You can see here that we did not use hexadecimal but normal decimals, but in case of bytecode, this is 20. 20 is like hexadecimal representation of number 32 in decimal. So we again pushed 20 in hexadecimal. Now we are pushing 0, and we are calling return. Return takes 2 values from stack. First, it's offset, the memory offset where it has to start, and 20 is length in memory of bytes that it has to return. So when we go here, okay, this is the end. So we can see that our return value is 42 because, well, we set EVM that it has to return this value. And this is one of the most simple programs that you may have inside of EVM, but it shows you more or less how EVM treats the code. Next up, let's quickly look at message calls. So EVM, apart from doing calculations inside of single smart contract, it can send messages to other contracts by call, delegate call, call code, or static call instruction. However, there's a limit to that. You cannot have call stack bigger than 1024 levels. That means you cannot call 1024 times or more because the execution will just revert. This is kind of protection to not exploit the EVM. However, in real life, this is not very realistic to have such a long call stack. And this is because of the diminishing gas being sent with every call, and we will talk about it a bit later. So how it works. First, we are putting into stack all the elements that are required in the call. You are putting into memory the call data that you want to pass, and then you are executing the call instruction. And the call creates the new call context for you. So it creates new stack and new memory and calls new smart contracts. And then you are executing the calling smart contract the same way as you executed the first one. But now you have the new call value, new stack, and new memory. And after execution of the called smart contract ends, it returns to the calling contract, and it returns by using return instruction. And return instruction, as we already saw in the EVM codes playground, takes a parameter of memory offset and memory length to be returned. And finally, we are reaching gas and fees. So EVM uses gas as a measure of computational complexity. And you can imagine gas the similar way how it's treated inside of the car. So your car takes more or less the same amount of gas per mile, but the gas price on the gas station may be different. The same thing is here. Each time you are doing any calculation, you are adding something, putting something to memory, executing different operation, you will use the gas. So when you start transaction, you are setting the gas price that you want to pay and gas limit. And first of all, before executing, EVM checks if you really have the funds required to run this transaction up to the gas limit that you set. And then with every operation, it diminishes the gas that you have available right now until the execution of transaction either ends or reverts because there is no gas left. And EVM also have the concept of gas refund whenever you are removing something from the storage. This is the way how EVM hours people for removing storage, because the design is to store the least amount of the storage on chain that you can. So when the execution ends, you are awarded a bit of the gas for the amount of storage that you cleared. But here's the question: why do we even need gas? This is to prevent all the kinds of griefing attacks or denial of service attacks that you can think of. Imagine that there were no fees whatsoever, and you can like freely execute everything that you want inside of EVM. Just imagine the amount of hacks and griefing that it will introduce, like people using, for example, Ethereum to mine Bitcoin or anything, because if they did not have to pay anything for the transactions, they will just have like free execution, and this is not profitable to anyone. And as you probably know, the blockchain rely on the notion of economical incentive for all the parties using it. We will now quickly go to the example that we had before, and we can see here how the gas works. So total gas consumed, this is a bit misleading because we did not execute anything yet, and we already consumed 21,000 gas. Why is that? You have to know that each transaction in EVM costs constant value of 21,000, again, to prevent any griefings for the node operators, for validators. And then each operation costs some gas. You can see that current operation, which is push 1, it costs free gas. Okay, if we move to next step, you can see that our total gas consumed was increased by 3. Okay, next operation, we have again push 1, which costs again free gas. This added to our total gas. And now mstore, and the amount of gas consumed, but this instruction is a bit misleading, and we will go into a bit into that in the future episodes. But it said that it would cost 3 gas, but you can see that it burned 6 gas. Next two operations cost 3, and the final return operation costs you nothing. This is actually exception, and there are just a few of the opcodes that are not taking any gas. One of them is return, second of them is stop, we have revert, and we have invalid opcode. This is special opcode, so it actually ends the execution of the transaction, but again, we'll go into details of it later. And finally, what I would quickly want to go through are events and logs. So apart from the on-chain state of the EVM, you can also have off-chain part which are the logs. You can emit logs when executing transaction. However, you can use them only off-chain. There is no way of reading emitted event inside of the smart contract. And this is actually very useful for off-chain agents that are listening for any state changes on-chain, because logs are queryable and you can easily read events emitted by a smart contract in specific transaction. Okay, and that's all concerning high-level EVM design. Next, we will go into details into each of the sections that I described here, starting from memory location, so stay tuned.